Okay, so it's going. So this one is due tonight. Um, I'll move this so I can see their faces. Was there anything that tripped you up or was tricky on this that you need clarification on? Yes. I just was showing you, it's redundant. I'm just showing you different ways to do it. Yeah, so the sum product is just, I've got two columns. I want to use the sum product. So when I do sum product of two arrays, it takes every element in the array and multiplies, A1 times A1 and B1 times B1 and so on. And then sums them together. So that is this integration of two functions. It's the functions times each other and then integrated. So sum product is another way to do an integral. Yes. 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 And so here we have, like I've got wave function 21 in here, but let's just do 1 and 2. And so then, so notice this is integrating just n prime times m prime. Okay, so it should be 1. It's showing the normalization in the sum product. But if I took one of these and multiplied it over here, so now I have n times n prime, and it should be 0, and it is. Yeah. So you can play around with that. We do the same thing in the matrix multiplication, but we're doing both combinations together. So if I double click on this, you see it's the transpose of this block times this block. In closed parentheses times the delta x, which is up here. And I like that Excel color codes everything. It makes it so nice because you can see all of the different colors and everything. Now, sometimes it's confusing when you're trying to look at the formula and it's covering up some of the cells. And so what you can do is you can click up here. And when you click up here in this formula bar, it also color codes everything, but it doesn't, like, look up here. When I click up here, I don't get the formula down here. But if I click down here, if I double click, then you see the formula down here in the square. And sometimes that covers up what you're trying to look at. So it's not a super detailed trick, but if you click in the formula bar up there, then it doesn't cover up things down here. So this first panel, then we plot those. Do y'all have any problems plotting? Let me show you some things that I don't want you to do. Like if I'm going to plot this wave function, I select what I'm going to plot, I do insert chart. There's lots of options, okay? We can do, if you have a small amount of data points, use markers only and no line, okay? If you're going to use lots of marker data and you're going to lose track of what series is connected to what series, then it's okay to include a line. Then you would use this one here where you're just connecting the data points for the purposes of visualization, okay? But if you're plotting a function, don't use the markers at all. Just use this one where it's lines only, no markers. Okay, so this is the thing that I'm very, very emphatic on. Never use either one of these. You know why? Because it's smoothed. Yes, but if you use smooth, if you draw, here's a scientific principle. If you show somebody a chart of data and you draw a line or a curve on there, you're making a statement that you know the equation for that line. And you don't know the equation for that smoothed curve. Yeah. So what you're saying is this is a continuous line. So I can tell you the equation for any point between 2 points on that line, and you can't do that with the smoothed data. So I would avoid smoothed curves unless you did the smoothing yourself, right? Unless you can answer my question in your defense. I see a smooth line. Can you tell me the equation for that line? And you will say no. And I was like, right, because I told you in class not to do that. Yeah, so any one of these three here. So dots only, dots and lines, or lines. Now these, you're drawing lines, but it's a linear line between 2 points, and you can do that algebraically, right? You got 2 points, you draw a straight line. You could use y equals mx plus b, and you could tell me the equation for the line that connects those 2 points. But if it's smoothed, you have no idea what Excel is doing. Yeah. Okay, so that's a good thing. Um, there's one other time when you use a line chart. Line chart and scatter charts are different. So this is a scatter chart. A line chart is here, and it kind of looks the same, but it's not. The x-axis here is not data points, it's categories. So this is what you would use if you're doing dates. Like if you have data that's collected by date, and some of you will in your thesis, you want to use a line chart so that you can set the categories as dates. But like if you have a date, uh, like if you have like every day, and then you have 2 weeks off, and then you have a day, you've got an increment of 1 day between these, and then it'll just put that next day right next to it. Like it's not an x-axis where it accurately plots, the distance between the points. It's categories. Yeah. So line charts those are for category data. You can still have a continuous y variable like temperature or toxicity or whatever. You can have some y-axis variable that's continuous, but the horizontal axis is categories, and that's what you would use a line chart for. So don't ever use a line chart when you have x data and y data, data on both axes, that's continuous. You understand what continuous means? I can have any value between any two other values, right? Whereas dates, you have a date here and a date there. There's no half dates. There's no 1/3 of a date. Okay. So those are categories. Okay. And then there's the discussion questions down here. Change the n values, see what happens. When is n too high for this spreadsheet? You can look at the symmetry rules here, even, odd, even, and so on. And you can say, yeah, absolutely. When I have an even times an odd, I get an odd. And so, yeah. Okay, and then did you see the Kronecker delta? That's right up here, you better say yes. Now, if you had 1 and 1, it would all be the same. It would all be ones. That's just because you have the same wave function in both columns, and so that's a way to break this. But you're not, it's still, yeah. So anyway, that's 1 and 3. Yeah. So you can play around with it. Then we go into the Schrodinger equation. Any questions on it? Again, doing it 2 different ways. One with sum product, one with matrix multiplication. It's just, I'm just showing you 2 different ways to do it. Okay, and we have the first derivative, second derivatives. You can say something about those. Percent errors, we talked about that a little bit up here. So the n equals 1, we have 3% error, n equals 2. But what about 3? We could do 3 here, and we see it's 26% error. That's really bad. And so you can comment on the numerical integration errors. Then we get over here to the question. Yeah. Um, Now let me show you. So if I've got this selected now, I've got the matrix area selected here, and I click up here, and you can see it's only containing. I make sure I understand what you're asking. It's only inside the box. So here's the center of the box. So negative L/2. Let me just go make L something easy. Okay, let's fix this so that we can. So let's make it 8. Oh gosh, cancel. Okay, 8. Okay, so that's our new box length. And we select this. click up here. Now you can see 8. What is L over 2? 4. So this is minus L over 2 and L over 2. And these are the extra rows for our differentiation. But this matrix multiply is just inside the box. So this is the transpose of the psi, transpose psi, comma, psi double prime. Yeah. And of course we have the constants out front for all of this business here. So that's the 2 Planck's constant to convert the unit over to kilojoules per mole. The Avogadro's number for the per mole piece. And the Planck's constants in kilograms, so our mass needs to be in kilograms, and everything else works out.
So the function
Yes.
is the integral part.
Yes. Yes. So I don't have, like I just says using M mult, but this isn't the equation. But you can see it up here. Here's the M mult. And this is on the video, so you can go and check your work if you want. Yeah, so you can go in and you can see, you know, x4, x5, x6, 8 pi, pi. I put 2 pi's in there instead of making a square. And then I have some other thing in the bottom. Maybe that's the mass. And then M mult, transpose this block, comma, this block, and then times B13, which is the integral of the interval, the delta x. Yeah. So there's our M mult equation for the Schrodinger equation. And control shift enter. Yeah.
Sometimes
Okay. Yeah. Okay. Yeah, because it was not working, and then we tried it, and it worked. Yeah, in my office. Yeah. Yeah. So that's the Schrodinger equation, and the first derivative, second derivatives. You can comment on those things. Then we get over here to the spectroscopy piece, simulating the spectrum. So this is the third panel. So we can solve for the selection rules. Now it's really, I mean, it's kind of difficult to solve for selection rules when you just have 2 wave functions. So you got to try all the pairwise combinations if you wanted to, 1 to 2, 1 to 3, 1 to 4. So we could, oh, I cancel. Yeah. So we could do 1 and 2. So we see that the 1 to 2 is allowed right here. We can see also here that it's allowed, same value. So 1 to 2, and here's that transition dipole moment integral result. If we did 3, you say, oh, well, there's still a number there, but look, it's times 10 to the minus 32. So that's 0. Yeah. I have matrix, the M mult is sort of to 5 or 6 decimal places. I could have done that here too, to make it 0. Let's do 1 to 4. So that's 1 to 4, and it's 0.01. So that's non-zero. Okay. So that's allowed. What about 1 to 5? So, you know, this doesn't take long. Once you build a spreadsheet, you can do your selection rules and say, yeah, we get the same selection rules that we got from the analytical. What? Okay, yeah. Yeah, and so then 1 to 6, 0.0008. It's small, but it's not 10 to the minus 32. So there's a big difference between a small number and 0. Excel can't exactly hit 0. Sometimes it does, but anything like 10 to the minus 16 and smaller, I mean, that's what Excel's trying to tell you. This is 0. Yeah. Okay. So we can get the selection rules. We can do the even and odd multiplication rules. I don't know why this is an NA. Yes. What? Yes. It's 5.9 times 10 to the minus 32. Yeah. Yeah. So you do have to kind of look at that and go, you know, how bad is it? Okay, so that's the selection rules piece. You can answer some questions about that. That's why I say change the quantum numbers to play with it. What if we did, you know, we could put a 2 here and a 3 there, so you're doing still delta n minus 1 or plus 1. And again, it's going to be allowed, strongly allowed. So, but it's tedious to change them, you know. That's why with the big spreadsheet, we have 15 options and we can get all of them at once. Okay. And then we get into the spectroscopy piece. There's quite a bit in here because we need the the upper quantum number, the lower quantum number. Let's just do the fundamental, 1 to 2. Okay. So the upper is 2, the lower is 1. We calculate the energy. Notice up here, this is the analytical energy equation. So h bar squared, n squared over 8 ml squared. Okay. So we just use that. We use the two constants, the two h constants. We have n squared here, right there. N is 2, this an7 is n squared. This is Planck's constant in one set of units and Planck's constant in another set of units. So right here, let me make sure. Yeah, it's going over here actually to get those. Yeah, so we have Planck's constant in angstrom squared to cancel out the length, and we have Planck's constant in kilojoules seconds to give us kilojoules per mole. Then we have Avogadro's number too. So that's the analytical energy for state 2. This is the analytical energy for state 1. Here's the delta energy, the change in those two energies. And then here is converting it to wavelength. Okay. So we convert that over to wavelength in nanometers. All right, so that's our transition location. That's where our peak will show up at 702.6 nanometers. Now we need a Boltzmann distribution. So this is going to be the Boltzmann distribution of that lower state energy minus the lower state energy, right? So we're seeing relative to the lower state energy, what is this probability of being excited? Well, this is the fundamental. We're in state 1, so it's going to be a probability of 1. And so we see the Boltzmann factor is 1. We have the intensity of that peak, the I piece. Remember the absorption is BIG, Boltzmann times integral times Gaussian. So this is the integral piece. We pull that over from here. So if we do a 1 to 2 transition, it's right here is the transition dipole moment integral. So we just pull that over here. And then we have the spectral line width, 20 nanometers. And then we need to select the plot, like where to plot our spectrum. And so I put a formula in here. I guess you could look at the video here, just so that the peak is always on the chart. Okay, I took the transition wavelength and I subtracted 4 times the spectral line width. So I took the transition and I went 4 times that width over here, and then the ending wavelength is that transition wavelength plus 4 times the width. And so that the peak always has, it's always in the center of the spectrum that I'm plotting, And then here's the wavelength increment. And I have all of those values in here, all the way down. Okay. And you don't have to build any of this. All you really do is just need to change the yellow cells. But here's the peak that I get right at 700. 702.6, but it looks like it's right at 700. And then I can come up here and I can change 1 to 2. I could do, what if I do a not allowed, a transition that's not allowed, right? So you said, what was it, 1 to 5 you were curious about? 1 to 5. Okay, look, it still shows a peak, but does it really? I mean, 10 to the negative 33, it's technically showing a peak, but this is not an allowed transition. So even though you do this and you see, oh, there's a peak there, it's really not there. I mean, you're not going to see a peak that has an intensity of 10 to the negative 32. So it's not allowed. Yeah. And it's the only reason it's showing 1 is because Excel can't really calculate numerically an exact 0. It's getting close, but it's okay. Let's do the 1 to 2, 1 to 3. That's also not allowed, and you can see it's also 10 to the minus 33. Then we get to 1 to 4, which is an allowed transition, and now it's at 0.00. Well, 3 zeros and 2 fives. Small, but it's still there. Yeah, that's. Yes.
How do you get the
E0. Where's that?
copy says 74.18. Here's this 56.8. So how does that?
Oh, I changed the box length to 8.
Okay.
Yeah, yeah. That's so I just wanted a nice clean box for our picture. You know, when I was showing the -4 and +4 is the box width, and so I changed it to 8. And so let's see what happens. Oh, let's see if I can do this. Okay, what we're gonna do is we're going to freeze the panes. This is a good handle, a good thing to know. So I'm gonna put the cursor right here. See, the cursor's right here, and I'm gonna come up here and I'm gonna say View Freeze Panes. Okay. Now when I scoot to the right, look what happens. The left panel stays where it is, and I can scoot all the way over here because I want to get. Oh darn, my plot. I need to scoot my plot up here. Okay. So what I want to do is I want to look at this. I want to look at this. Let's do 1 to 2. Here's our spectrum. The peak's at 700. Here's my box length. And this is when I talk about playing around with the spreadsheet, this is what I mean. Now that I've built this thing, it's dynamic. It responds to all the yellow squares. Okay? So if I make the box shorter, what will happen to my peak? So we're shrinking the system, and the energy. Where is L in the energy equation? You right. So E of n is equal to n squared. That's the quantum number. H squared over 8mL squared. Okay. And remember that spectroscopy is the difference in energy levels. So if I make the L smaller, what happens to the energies? Yes. So they get further apart, right? From me drawing. We do this. L equals 8. Okay. What do you want to do? Go to 7? You see how they're farther apart? Right? I got to a smaller L, makes the energies go up. It also makes the differences go up. And what is spectroscopy? Spectroscopy is the difference between energy levels. Right? So this arrow got longer. What does a longer arrow do in wavelength? So this longer arrow is in the denominator. So what should happen to the wavelength? Shorter wavelength. So it should blue shift. It should go towards the shorter wavelength. So let's go from 8 to 7 and watch that peak. You see it's at 700 nanometers. Y'all are telling me it's going to go to a smaller number. 7, we hit it. It did. It went quite a bit. It went from 700 now to 540 or something like that. Yeah. Isn't that cool? That's exactly what happens in nature. You get a smaller molecule, all your peaks go into the UV. Right? They're colored molecules, big, long, extended chains, but if you shrink that molecule, those transitions move towards shorter wavelength. So I think that's one of the questions down here. Change the quantum states, change the box length, right? Freeze panes, I just told you how to do that. Um, and then your high definition workbook, let's see. You don't have access to that. Don't worry about this question really. That's the one you're going to build. So this is an assignment that I give the undergrads in their lab, and so I give them the high definition version. They don't build it, but you guys are going to build it. So this is the high definition one. Now, same thing happened. So we had 8, and our fundamental was at 700. You see here on this high definition one, look how nice and clean it is. Here's my fundamental at 700, the box length of 8, and an electron. We're going to change that box length to 7. Sure enough, that dropped from 700 to 540 or 550. So same thing. The big version and the little version give you the same answers. That's nice. Okay.
Just know the very first part, one day after that, it says where the
Oh, in here, one of these questions?
no on the one hand, yeah, it's in the where the way
Okay. Go this way? Okay, K16. Okay. K16. Yeah, this. Yes. Yes. Uh, oh, yeah, I see what you mean. Yeah, yeah, yeah. I see what you're saying. Yeah. Um, okay, maybe I need to improve the instructions. Yeah, 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 yeah. Yeah, I need to think about how to say that. Yeah. Okay, thank you. Yeah. Okay. So any more questions on the small spreadsheet? You had some the other day. Did everything work out?
Base spread, all my questions are from the base spreadsheet. I've been working on it.
Okay.
Other than that, I have.
Okay. No, I'm just making sure that you were getting everything that you needed.
Just by reaching the distribution, that doesn't require this.
Mhm. Okay. So let's go to the big spreadsheet. And I've got some new panels on here that I added last night, just to show you the difference between the Gaussian, which is shown here, the Lorentzian, which is shown here, and the log normal, which is shown here. So I've added a new term called the asymmetry parameter here. If I make this 0.99, almost 1, you can't make it 1 or it'll go away. So they're symmetric now, or very symmetric. And so you see the very similar spectra, but you see that the Lorentzian, it has a wider base. And so it doesn't go to 0 as quickly. And so you see that even though these two peaks are very far apart, here they're the same distance apart, but they still have non-zero absorption. And so you see that doesn't come all the way to the baseline, when you add them all together like it does here or like it does here. Okay. So that's kind of interesting. So one of your options is to change, this Gaussian function, which we used in the base model, to then copy this sheet over and change that Gaussian function, which is in here, this guy right here, the exponential, the Gaussian function, to change that to, say, the Lorentzian function, and then model it with the Lorentzian line shape. Notice how the spreadsheet looks exactly the same, but we just have a different function for each of the peaks, a different line shape. And so that's something you can do as an option, when you get to that last part where you're now taking it and extending it a little bit. That way it's not just a cookbook. you just follow what I tell you to do and then turn it in. Well, it's not a lot of, there's some learning there, but not a lot. Then when you could take ownership and say, okay, now I get a choice. I'm going to make a log normal, or I'm going to make a Lorentzian line shape. How would I do that? Then that makes you understand what's going on in the spreadsheet. Okay. And then here's the log normal. Now there was a couple of tricks I had to do for the log normal. And this is the most complicated equation we've seen so far. The log normal gets so close to zero, or I would say this difference gets so close to zero inside the log that it starts throwing errors, you know. So you can calculate the natural log of small numbers, but if they get too small, then the log runs to negative infinity, and that's a problem. You get an error. So I had to incorporate what's called an error trap. Okay, and this I'm putting it on the video in case you want to do this. Notice I have an if-then statement here for my line shape. And I'm saying if this throws an error, see this function called isError? And I open it up, and then I put the log normal line shape in here, inside that. So that's the equation for the log normal line shape. I put that inside this error trap that says if this throws an error, then, so an if-then statement has if, a condition, comma, what to do if it's true, comma, what to do if it's false. Okay, so it's three things. The condition, what happens when it's true, what happens when it's false. So the if then sets this up. If the condition is, does this equation throw an error? Yes, make it 0. If it doesn't throw an error, then calculate it. So I repeat the, if isError, if that's true, then I say just put a 0 in that cell. If it's not an error, then calculate it. So this is the line shape function. It's a little clunky because you have the line shape function in there twice. Once is just seeing if it's going to throw an error. The second one is actually calculating it. If it's not going to throw an error, calculate it and put that in the cell. Then you close parentheses. Yes. It's going up today, so I'm recording it now. Yeah. So, yeah, that's good. So that's a little advanced, but it'd be great if you knew how to do if-then statements and error traps and things like that. So if you want to do that one, that's great. So it gives a really good line shape, and you also have to refer to this asymmetry parameter. Let's see, which is given right here, and it just refers to that control page. You can have it refer to this front control page where the asymmetry parameter is given. Now, what I did was once I make these charts, then I just copy them. I hit this. I hit Control C, and then I go to the control page and I hit Control V and paste that chart on the control page. And so it's referring back to that sheet, but now I'm on the control page and I can change the box length and the mass and everything and see what happens to the charts. Okay. So I'm going to delete that one because I've already got it. Okay, let's look at the log normal and have some fun with it. Remember, it's from the center, you have a high width and a low width, and it's the fraction of the high to the low. So if we want this to tail to, to the left, to short wavelength, then we need asymmetry parameters that are less than 1, because the high wavelength side will be small and the short wavelength side will be big. So if we make it 0.5, see, it tails to the left. And that's saying that this piece right here is half of that piece. That's what the asymmetry parameter is. And you can see it is. It's this piece right here is about, if that's 1, this is 2 units. That's the asymmetry parameter. What if we made it 2? Let's make the asymmetry parameter 2. Now, this side is 2, that side is 1. So it's the high side divided by the low side. And it's kind of interesting to see, here we have a peak here, a shoulder, and a big peak, right? With the this we start to see some other little bumps, right? It's kind of interesting to see that the line shape, it's the same data, it's the same box length, it's the same mass, it's the same everything, but different line shape. And so how the system responds to you know like your spectrometer or whatever, you know, you get these different line shapes. Let's see, what else would I want to say? You can play around with the spectral line width. So we're at 100 nanometers. It was a really crummy spectrometer. A really fast one, maybe a USB. They make spectrometers that are on USB drives, like that small, you know, and with a little fiber optic that comes out. And it's super great for like agriculture. You can have a laptop on your little four-wheeler, and you can have this fiber optic, and you can take the, you know, leaf color or whatever and determine how healthy your plants are. Yeah, out in the field, and collect all that data. So let's make it a better spectrometer. What number should I put in instead of 100? 10. Okay, high resolution. Yeah, so we've got really sharp peaks. Everything's resolved. Not everything though. You get down here where they're really close, and you can kind of see it's not resolved. Let's make a crazy bad asymmetry 5. Okay, you can see them all pale out. Yeah. So this is fun. Have fun with your spreadsheet. You spend a lot of time building it. Don't just turn it in and go, okay, I'm done with that. Play around with it. That's what it's for, right? And so then 10. Let's say we don't have the kind of money to get a 10 nanometer spectrometer, and let's go 50. Yeah. And so we still see some added intensity here where they're not resolved, you know, but we get more of these little bumps in this, because we have that sharp drop. And so when we have those sharp drops, then we can identify more of those peaks. It's kind of neat. Let's go to an asymmetry parameter. If it's 5/1, what is 1/5? That's 0.2. So let's just take that same line shape, but just flip it the other way. So let's put 0.2 in here. Boom. So that's a totally different looking spectrum. But what's weird to me is that's just a different line shape. It's not the different particle size. It's not a different mass. And so it really helps us, this spreadsheet really helps us discern, you know, how you can get a very different looking spectrum with a different line shape, even though it's the same molecule, if you will. Let's talk about that. So we have a box length of 7. I like 5. That was fun. Okay, we'll stick with 5. Let's go to let's have a really, like, let's not go to a proton, because that's such a dramatic change. That's a factor of 1,000 change in mass. Okay, so let's just make a skinny electron. Okay, let's just go from 9.1 times 10 to the minus 31 kilograms to just 9. Okay, so he's just a little bit skinny. So 9e minus 31. Did you see how I entered that? I don't have to type out, you know, 0.00000. I can use scientific notation. I don't have to do times 10 with the caret sign. I can just do e minus 31, and it will understand that as scientific notation. Okay. Well, I didn't see what happened. So maybe that wasn't enough change. Let's undo that. Yeah, there was a little shift. But let's go to 8. Okay. Now what should happen? Here we are. Mass is in the denominator. So we're going to go from 9 to 8. Yep, higher energy. Okay. So that means energies are going to be farther apart, which means our wavelength is going to get, our energy difference is going to get bigger, which means our wavelength is going to go down. So we should see a blue shift. So we'll go to 8e minus 31. Watch the peak. Pick one. I see this one on the Lorentzian curve. It's at 54 or 540. So yeah, it dropped a lot. Yeah. So that's cool. All right, let's do undo. So we're back to an electron mass. Now, why do we see, so here we're at 7, we're going to go to 8, okay? What do we see in just, again, this is a particle in a box, we're working in a spreadsheet, but it gives us intuition. What do we see in space as the universe gets bigger? What is our evidence that we have an expanding universe? Yeah, but what does that do spectroscopically? Like if we're looking at a star, what does it do to the light coming from that star? Right, so let's go from a universe that's a 7 to a universe that's an 8. Redshift. So as the system gets bigger, we should see a redshift. Everything from a particle in a box, an electron on a wire, to the universe obeys the same physics. Yeah. So that's neat. Yeah. Now some of that is really not necessarily redshift because it's in a box, but because of the Doppler effect. As it's running away from us, the wavelength appears to be redshifted. Yeah. But it's still a good intuition to have. Yeah. Okay. So that's the high definition spreadsheet. Let me do one more. You don't have to do this one, but this would be an option too. If we were to take this X psi here, which goes over and gets this, X psi spreadsheet, what if we were to go to that X psi spreadsheet and make it X squared? So then we would be doing a Raman experiment where a photon comes in and interacts with the x-axis, and it also leaves interacting with the x-axis. So that's scattering. And so that'd be the x squared or scattering selection rules. We didn't ever do those analytically, but they are in the book. I think that's chapter 5. If you go through chapter 5, you get the Raman and Rayleigh scattering rules. So here we have that. Let's see. No, not number 6. Okay, first, we've got time. Yeah, okay. So let's do this. Before we get to that one, okay, cancel. Let me do it, please. If I ask nicely. Yeah. Copying the file. I'm not copying anything. Skip. Okay. Oh my gosh. I am really sick of the internet and this building dropping me off. I'm going to do a hotspot. I have to do a hotspot on campus. This is shameful. Okay. Okay. So let's try that a third time. Good. Good. Okay, so another thing too. Let's say you wanted to plot these spectra not by wavelength but by energy. So instead of a wavelength experiment, you had an energy experiment, and your spectrometer dispersed things based on energy. And our units that we have for this spreadsheet are kilojoules per mole. We could convert it to wave numbers. We could convert it to anything proportional to energy. But all of our peaks would be switched. So this now is the fundamental. The first peak here is on the left now, and it drops off. And look at all of these little guys here. These are all of the ones that are super small, the overtones, and they're really spread out in energy. Okay, so let's, so all I did was I changed this, instead of wavelength, it should say energy here. Okay, and plotted it. I also had to change these little guys. Instead of the wavelength, here, they were plotted the stick spectra, but instead of plotted by wavelength, they were now just move this up to energy, and they all switched. Okay, and then I went and I changed what this one was referring to. Instead of referring to wavelength, I moved it up and referred to energy, and then copied it over and copied it down, and that's all I had to do. Now all my spectra are flipped and they're plotted versus energy. So that's pretty cool. On the control sheet, we have all three of these now plotted versus energy, and you can play around with that. The reason I show you this is because I did the Raman selection rules, and Raman is typically plotted versus wave number or Raman shift, which is an energy axis, not a wavelength axis. Okay, so I wanted to show you, yes, you can flip these to energies. So I did this to energies plot, and then I did the Raman selection rules. So let me show you the Raman selection rules, and then we'll be done. I've got 1 minute. Hang with me. Okay, so Raman versus energy. Running through my hotspot. Yeah. Okay. I'm glad I have a fast phone. Okay. So here, I want to show you this. It worked. Okay. So here I've got the x2. So x squared. So here now, x times the wave function, I've got x squared times the wave function. So that's all I've changed on this sheet. Instead of x psi, it's x squared times psi. Okay. And then I did this. The selection rules are different. This isn't absorption. Can you tell me by looking at this block of numbers what the selection rules are for scattering? Should I zoom in? What are the selection rules for scattering? Delta n equals the non-zero things. Yeah, let's start with the first one. 1 to 1, that's a delta n of 0. So there, 2 to 2, 0. You know, it's non-zero, so that's a good one. Delta n is 0 here. Also, this result is non-zero. So delta n equals 0. That's Rayleigh scattering. So this diagonal here is the Rayleigh scattering, and then the delta n of 2's. So 1 to 3. That's a delta n of 2 is non-zero. Delta n of 4 is non-zero. So all the selection rules flipped, and I didn't have to do all the calculus. The absorption calculus was 4 pages. The Raman calculus was 6 or 7. So you had to do integration by parts twice. It was nested. It was a disaster, but we got through it. And so these are the Raman selection rules. The other thing is the Rayleigh peak is a delta n of 0. And so its energy, where it shows up, is going to be a 0 energy shift. So it's going to be right on 0. So this spectrum has a peak at 0 that's really, really tall. So let me go to the control sheet. You see, there's a tall peak where the delta n equals 0. So that's 1 to 1, and 2 to 2, and 3 to 3, and 4 to 4, all on top of each other. So there's a huge Rayleigh scattering peak, and then these are the Raman transitions. Yes. And so these are all delta n equals 2's. Okay, so this is 1 to 3, 2 to 4, 3 to 5, and so on. All of these delta n equals 2's. And then these are the delta n equals 4's and 6's and 8's, but their intensity is just really small. So you can do Raman spectroscopy in this little guy too. And then that's another option for your extension. Yeah, all it did was change from x psi to x squared psi. And it worked. And I changed the energy. I plotted versus energy, not versus wavelength. So it's 2 changes to the big spreadsheet, and you're doing Raman. Yeah. And we can talk about this more on Friday. How about that, since we're out of time? Okay.